Okay, so there's the list of Platonic graphs from the 5 Platonic solids. So let me explain what these numbers are. So n is the number of vertices. Maybe I'll write this in a moment. This is probably the last slide. N is the number of vertices, obviously. So 4 tetrahedron, 8 vertices cube, 6 octahedron. There's this duality. So a cube and an octahedron are dual. You've got the number of edges, but skip the number of edges to the number of faces. So to get from a cube to an octahedron, you swap vertices and faces. So 8, 6 becomes 6, 8. Similarly, dodecahedron has 20 vertices, 12 faces. 12 dodecahedron means 12. You swap those to get the icosahedron, which has 12 vertices and 20 faces. And they both have the same number of edges. These two and these two have the same number of edges. What are P and Q? Well, I'll write this down in a moment, but P is the number of edges bounding a face. So tetrahedron has triangles, so there are 3 edges. Cube has squares, so 4 edges for each face. Octahedron has triangles again, so 3 edges. A dodecahedron has 5 edges to each face because they're pentagons, and an icosahedron has 3. And again, you swap. Q is the vertex degree. So Q, these are regular graphs, so every vertex has the same degree. So Q is the same thing as what we call delta. It's the maximum degree of each vertex. And you swap P and Q in the dual cases. So again, a tetrahedron, 3 edges meet at each vertex. That's why it's dual to itself. You can't get anything dual. If you put vertices in each face of the tetrahedron and join those, you get a tetrahedron again. But if you put vertices in the middle of the square faces of the cube, you get the octahedron, which explains why these swap over. Chi is the chromatic number, and we already checked that today. So the tetrahedron, it's the same as the complete graph K4. So it has chromatic number 4. The cube is bipartite, 2. The octahedron and dodecahedron are both sort of nice graphs. They have chromatic number 3. The icosahedron is a bit more complicated. It has chromatic number 4. But they're all planar graphs, so we can't see a number bigger than 4 here. Now, Eulerian is easy because that's a matter of what is the vertex degree. And you see all the vertex degrees are odd. Vertex degree is Q. They're all odd numbers apart from the octahedron. So the octahedron is the only Platonic graph that has an Eulerian cycle. So it's easy to remember. It turns out they're all Hamiltonian. Rather interesting. So every Platonic graph has a Hamiltonian cycle. That means a cycle that goes through every vertex. And I'll draw them in a moment. So someone asked me, what's the difference between a cycle and a complete graph? A cycle is just a graph. To say, for example, the dodecahedron is Hamiltonian, that means that inside the dodecahedron there's a subgraph that looks like a necklace that goes through every vertex exactly once, and it doesn't go through the same vertex twice. So it's like putting a necklace inside, a closed necklace inside the dodecahedron. Inside the dodecahedral graph, and you could do that. And it has to be a cycle that goes through every vertex exactly once. There are 20 vertices, so it will be a 20 cycle. A necklace with 20 beads, well, let's say 20 bits of string. These are all Hamiltonian graphs. Here's a picture, actually, then I'll do it on paper. There's a picture of the more complicated, the dodecahedral graph on the left and the icosahedral graph on the right. They're both plane diagrams. There are no edge crossings apart from at vertices, so that shows they're plane graphs. The dodecahedron is sort of... Now, you won't be asked to draw these from scratch. I think there's a problem on the sheet asking you to copy the dodecahedron. But you should be able to draw the dodecahedron at least from scratch, because you just start with the pentagon in the middle, then you add a ring of pentagons, that's easy enough, and then you just remember to put the outside pentagon, which gives you 5 more pentagons, not regular in this diagram, only the middle one's regular. But you can nonetheless, you see the middle pentagon, this ring of pentagons here, the bottom ring of pentagons, and there seems to be a pentagon missing, but that's the outside region. Because when you draw these solids as graphs, one face becomes the whole outside of the graph. So when you count faces, you must remember to count the outside, otherwise you'll make a mistake. So there should be 12 faces here. Well, if you do it naively, there's 5, there's 1 in the middle, 5 round that, that's 6. Another 5 round the outside, that's 11, and it should be 12, but the 12th is the outside region. Similarly for the icosahedron, you'll get 20 faces if you include the outside, but there are only 12 vertices. These are all triangular faces, but the degree of each vertex is 5. Okay, let's check the Hamiltonian. Let's do the dodecahedron first. So supposing I start at this vertex, I've got to go all the way round, maybe I can use this pen here. I've got to go all the way round through every vertex exactly once. Now, let's suppose I come back, it's sort of all equivalent, so it doesn't, I mean, I'm going to walk off in this direction and I want to come back here. So maybe I'll sort of try and come this way somehow and get back to where I started. I've got to finish from where I started for my Hamiltonian cycle. Well, let's do the whole outside as much as I can. But I have to go inside there, otherwise I'll be stuck, because I can't go through this vertex more than once. So I then go inside, and then let's try and do the inside pentagon. I'm cheating a bit because I did this before. And then I've got to do the inner pentagon. The edges don't matter, it's covering each vertex that matters. And then I can do it all, right? I think I've covered every vertex exactly once. Okay, and there should be 20 edges. There should be 20 edges in this cycle, okay? So this is the 20 cycle. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is a 20 cycle, so it must be Hamiltonian. It's a necklace, if you like. It's a necklace. It's a subgraph. It's a subgraph because I'm including every vertex, but not every edge. If you leave out edges and or vertices, you'll have a subgraph. That's a 20 cycle inside the dodecahedron. Now the icosahedron should be a bit easier actually, because there's so many edges. There's so many edges coming out of each vertex that you can't really go wrong. You don't have to be too careful. So if we start at this vertex, I can go up there. I don't have to sort of come in yet. I can go all the way down to 2, because I've got lots of escape routes here. And then from 2, what have I done? I've gone up to try and do the hexagon on the inside. So I do this. And then I've got this triangle in the middle, which I can do this way. Then I go to 6, and then I can escape through 7 back to where I started. And that should be a 12 cycle covering all 12 vertices. 1, so I'm starting and finishing there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a 12 cycle. Inside the icosahedral graph. So that means that they're both are Hamiltonian graphs. Obviously it's much easier to show that the other Platonic graphs are Hamiltonian. Okay, But it can be harder if you have some of these special graphs which are Hamiltonian. It might not be so easy to check that they are or to prove they're not. Remember, the Peterson graph is not Hamiltonian. Don't know how easy it is to prove that. Nor is it so, I don't know if it's so quick to find a cycle for the Groch graph, which is Hamiltonian. Okay, any questions? Okay, let me then put the table back and make some more comments on the numerics. So we've actually done the fact that I've shown you that two of them are Hamiltonian. It's easy to do the others. Well, you already know that K4 is Hamiltonian. It's pretty obvious that these cube and octahedron are Hamiltonian. You can check that. Eulerian, I've explained why only one can possibly be Eulerian, because it's a problem. It's a question of the vertex degrees. So I'll give you the definition of P and Q now, but that explains why only one of them is Eulerian. So n is the number. I always use n to be the number of vertices. I use little e to be the number of edges. These are all simple graphs, so there's a set of edges, of distinct edges. This is the number of edges, my graph, or of the polyhedron. F, you have to be careful. F is the number of faces of the polyhedron, but it's the number of regions of the graph, including the outside. So this is the number of regions, if you like, of the graph, including the outside region, the infinite region. So it's faces of the polyhedron, but when you do the graph theory, when these become planar graphs, so these are all planar graphs. I haven't really justified that, maybe I will in a moment. These are all planar graphs. They can all be written in the plane without crossings. And that's true for any polyhedron, actually. P is the number of edges bounding each region, whether it be inside or outside. Q is the degree of every vertex. They all have the same degree. Degree of any vertex, or of every vertex. Of course, they're regular graphs as well. The vertex degrees are all equal. So this, therefore, is equal to delta, because the maximum will be the same as the degree of any vertex. So that helps you explain a bit the chromatic number, maybe. So that means the chromatic number should be less than or equal to. So the chromatic number will be less than or equal to delta, except for K4, which is the tetrahedron. Because the tetrahedron is K4. The same thing. So by Brooks's theorem, as long as it's not a complete graph or an odd cycle, so we have to forget the first one because that's a complete graph, we see that the chromatic number is hopefully less than or equal to the vertex degree delta, which is correct. So remember, this is a complete graph, so it's sort of exceptional from the point of view of colouring. So chi is the chromatic number. That's obviously that. I've assumed you understood that already. And that's the explanation of the table. But why do we only get these possibilities? Well, I could almost explain that for you by a very neat trick. So forget the table, look at the definition here. And you know, of course, that if you take in any graph the vertex degree, we know that in any graph, if you take the vertex degree, well, we know what was the general formula. We know that the sum over the vertices of the degree of each vertex in any graph is equal to twice the number of edges. So in our situation, the vertex degrees are all equal, and if there are n vertices, we get n times the vertex degree, which here I'm calling q, and so that has to equal 2e. So nq should be 2e. Okay, well, we can check that. N times q, 3 4s are 12, 3 8s 24, 4 6s 24, 3 20s are 16, and so on. So that works. But we can do an analogous thing with P. You see, if we have a number of regions, and every region is bounded by P edges, we can say similarly, if we take the number of regions and multiply by P, that will give the number of edges, except that each edge bounds two regions, one on the left and one on the right. So 2fp will also be twice the number of edges. Okay, that's because each edge, this is counting edges by faces, or by regions. But in a planar graph, this only makes sense for planar graphs, in a planar graph each edge has a region one side and a region the other. So we have those two formulae. So here are the two formulae to remember. This is for planar graphs, okay, so this is for planar graphs, for regular planar graphs. Well, let's say not only regular, but we need all the faces to bound the same number of edges. So for the Platonic, let's say just for the Platonic graph. Now, Euler's formula, which I haven't proved yet, but I think I've mentioned it. Euler's formula for a plane graph, I haven't even defined formally planar graphs, but they're graphs, as you know what they are, that you can draw without edge crossings in the plane, is number of vertices minus the number of edges plus the number of faces is equal to 2. This 2, if you do geometry of surfaces, corresponds to the so-called Euler number of the sphere, actually. Now let's substitute let's multiply that by PQ. So that's NQ times P minus EPQ plus F times PQ, F times P times Q, is equal to 2PQ. That's clearly correct. But I told you that NQ is 2E and FP is 2E. So that means that the number of edges is equal to 2PQ divided by 2 into P plus Q. So I've got P plus Q minus PQ. Agreed? That's a formula for the number of edges in terms of P and Q. I suppose you could check it with the table, but I'll assume that it works. Now, the number of edges is positive, obviously, so that tells you that the denominator is a positive number. So P, let's write it back, I don't really need the brackets here, 2P plus 2Q minus PQ has to be strictly positive because the whole thing has to be positive. And that implies that if I factorise P minus 2, well, that implies, first of all, I can negify this inequality and get minus 2P minus 2Q plus PQ is negative. You must change the sign if you multiply by a minus number. So that implies that P minus 2 times Q minus 2, that gives me most of this bottom line. I've got minus 2Q minus 2P plus PQ, but I get plus 4. So if I add 4 to both sides here, plus 4 is less than 4. This is less than 4. That's the conclusion. So I've gone from there, then I've just negified it and added 4 to both sides, and that's the same as this product, this inequality here. Now take P and Q. P and Q, I mean, we don't want to have vertices of degree 2. They're not useful. We want every vertex to have degree at least 3. We need at least triangular faces. We can't have a face with just 2 edges, so these graphs are simple graphs. So we can assume that P and Q are at least at least 3. So P and Q are greater than or equal to 3, otherwise it's not going to be useful. But I'm trying to classify the Platonic solids, or the Platonic graphs. So there aren't many possibilities left if you look at it. In fact, I think I can even fit it into this little space here. So what can P and Q be? Well, P's got to be at least 3. If P is 3, then this is 1. So if P is 3, then Q minus 2 has got to be less than 4. Okay, so Q could be 3, or it could be 4, or it could be 5. Agreed? Because in every case, the product is less than 4. For example, P 3 minus 2 times 5 minus 2, that's 3, which is less than 4. If P is 4, then this becomes 2, and the only thing Q can be is 3. Can't be anything else, because if Q is 4, if they're both 4, I get 2 times 2 is equal to 4, that's not less than 4. If P is 5, and this is 3, Q has to be at least 3. Q can't be 4, because I get 6 is less than 4, so Q would have to be 3. And if P is 6, I'd have 4 times something is not less than 4. So those are the only possibilities. Okay? So I have 5 possibilities. And they correspond to the 5 Platonic solids. You could have both of them 3. Here's the table. You can have both of them 3. That's the tetrahedron. You can have P is 3 and Q is 4. That's the octahedron. You can have 3 and 5. That's the icosahedron. 4 and 3 is the cube. And 5 and 3 is the dodecahedron. Okay, so that's I've almost sort of explained to you why there are only 5 Platonic solids using the graph theory. All right.